Hello, my name is Devin Lucas. I am a senior at Colorado State University, and this video is for my multimodal interaction for 3D user interfaces class. I'll be discussing the current status of my capstone from a technical perspective, as well as showing a demonstration of the current working prototype. The capstone investigates flight-based locomotion techniques within world-scale virtual reality environments. I'm using Cesium for Unity to stream the Google Photorealistic 3D tiles, which reconstructs Fort Collins, Colorado, as a photogrammetric testbed for locomotion experimentation. The first locomotion method I've implemented is what I'm calling Viltrumite flight, named after the superhuman flight style from the Invincible comic and television series. The core mechanic is simple. Make a fist and you fly in the direction your hand is pointing. Open your hand and you decelerate to a hover. Let me walk through the two scripts that power this locomotion system. The first script is fistdetector.cs, which handles gesture recognition for the fist pose. This script accesses the XR hand subsystem to monitor skeletal hand tracking data. The detection logic differs from what I implemented in assignment 1. Here I'm measuring the physical proximity of each fingertip to the wrist. The script iterates through 4 fingertip joints, the index, middle, ring, and little fingers. For each fingertip, it transforms the tip position into wrist local space, then checks how close that tip is to the wrist center. If a fingertip falls within the curl threshold, which defaults to 5 centimeters, that finger is considered curled. When at least 4 fingers meet this criterion, the hand is classified as a fist. The script exposes 2 public Boolean properties, is right fist and is left fist, which other scripts can pull from each frame. For debugging purposes, the script also modulates the hand mesh color when a fist is detected, turning the hand green. This provides immediate visual feedback during testing. The second script is viltrumitecontroller.cs, which consumes the fist detection state and translates it into locomotion. When the right hand forms a fist, the controller calculates the distance from the wrist to the head. This arm extension value determines how fast you fly. If your arm is close to your body, you hover in place. As you extend your arm outward, your target velocity increases proportionally. The flight direction is determined by the right wrist forward vector, meaning you fly wherever your fist is pointing. To create smooth, cinematic motion, the controller uses exponential smoothing for acceleration. The time constant is set to 0.85 seconds, which means you reach roughly 95% of your target speed after about 2.5 seconds. This prevents jarring, instant acceleration and gives the flight a more natural, weighted feel. When you open your hand, the controller applies a deceleration rate that gradually brings your velocity to 0, rather than stopping abruptly. The script also enforces altitude-based speed limits. Near the ground, your maximum speed is capped at 40 meters per second. As you climb higher, through discrete altitude tiers, the cap increases, reaching up to 20 kilometers per second at extreme altitudes. This prevents you from flying dangerously fast through dense urban geometry, while still allowing rapid traversal at altitude. Finally, there's terrain floor enforcement. The controller casts a ray downward to detect the terrain surface, then prevents the XR origin from dropping below a minimum offset above that surface. This keeps you from clipping through buildings or flying underground. Beyond the script, significant work occurred in the Unity editor to configure the scene hierarchy. I have prior experience with Cesium for Unity from a personal geopolitical intelligence application I've been developing. That familiarity accelerated the initial integration. The scene is built around a Cesium georeference component, which establishes the geographic coordinate system with Fort Collins as the origin. The XR origin is parented under this georeference and includes a Cesium globe anchor for proper world space positioning, plus a Cesium origin shift component to handle floating point precision at large distances from the origin. I initially experimented with Aerometrics Denver high-resolution tiles alongside Google 3D tiles, but the combined tile streaming introduced performance issues. I've disabled the Aerometrics tile set and plan to move forward with Google tiles exclusively. The tile set parameters in Viltrum Scene are tuned for locomotion at speed. I've increased the maximum screen space error to 16, reduced simultaneous tile loads to 5, and constrain the cache to 1 GB to accommodate Quest 2 memory limitations. To deploy the application, I built an Android APK from Unity targeting the Quest 2, then push it to the headset. I recorded this demonstration using MetaQuest Developer Hub's screen recording feature. So here, the user spawns in above Canvas Stadium. You can see a clenched fist navigates you downwards, and as you move closer to the floor, you decelerate, and when you open your hand, the movement stops altogether, and you can look around freely. When you open your hand and you raise it above your head, you'll climb slowly at first as you're raising in altitude, and then the speed will gradually pick up as you get further above the terrain. As you can see, there is no movement that takes place when a fist is detected with the left hand at this time. This is reserved for possible future implementation. When you turn your fist to the right, you go right. When you turn the fist to the left, you go left. Your top speed increases exponentially when you reach higher altitudes, as you can see by how fast I move towards Horsetooth. A few things I'm planning to refine after this checkpoint. You may have noticed the hand rendering is quite shaky, almost like the hands are shivering. I'm currently investigating the cause of this instability. I also plan to implement geographic bounding for the Cesium tiles, constraining the renderable area to Fort Collins and its immediate surroundings. This should improve graphics performance and allow for higher visual fidelity within that bounded region. Finally, additional locomotion methods are being planned for future checkpoints, which will enable comparative analysis between different flight paradigms. Thanks for watching.